Okay, in this video I'm going to attempt to solve some HackerRank problems at the medium difficulty. In the previous video we worked on, I think it was 3 easy problems in about an hour or so. This time I'm also going to work for an hour. We'll see how far we get with a medium problem. And I expect these to be quite a bit more difficult. So let's do Queen's Attack 2. Okay, so we're given a square chessboard with one queen, a number of obstacles. Determine how many squares the queen can attack. And I'm going to start the timer. Okay, so we have an n by n chessboard, rows numbered 1 to n going from bottom to top, columns 1 to n going from left to right. Each square is referenced by a tuple describing the row and column where the square is located. The queen is standing at RQ, CQ, and in a single move she can attack any square in any of the 8 directions, left, right, up, down, and the 4 diagonals. So she can attack all of these green circles when at location 4, 4. Okay, so we have like a 2-dimensional array type structure, so like a square matrix that is 1 indexed, so that's a little bit of a curveball, but just need to make sure that we don't have, or that we watch out for off by 1 errors. And so we have 8 directions, the 4 orthogonal and the 4 diagonal. And there are obstacles on the chessboard, each preventing the queen from attacking any square beyond it on that path. So for an obstacle at 3, 5, the queen can't attack 3, 5, 2, 6, or 1, 7. Given the queen's position and the locations of all the obstacles, find and print the number of squares that the queen can attack. So here we have 24 squares that she can attack. Apparently, we get the number of rows and columns on the board, so we're always dealing with a square board. K is an int number of obstacles. RQ is the number of the queen's position. CQ is the row number of the queen's position and the column of the queen's position. Obstacle is a 2-dimensional array of ints where each element is an array of 2 integers. And the row and column of an obstacle, so we get like a list of tuples, if you will, I guess. So we have a tuple, well, we have 2 ints, one for the queen's row and column, which can be represented as a tuple that we can use to index into this 2-dimensional array. I think we could represent the board like that. There's probably, well, there's certainly much more efficient ways to probably represent the board. I don't know much about actual chess programming, but I think that they use string representations for boards, like bit boards. I'm probably not going to be able to implement that, but we can definitely implement this as a 2-dimensional list of lists in Python, I would say. Constraints, n is between 0 and pretty big number, and k is also the same size, so we can have an entire board of obstacles. A single cell may contain more than one obstacle, which doesn't really have any implications for the solution, I guess. If we had like 2 obstacles on the same square, it wouldn't change the state of the solution. Might have implications about the implementation, like if we're, depending on how we're looping, whether or not we can shortcut. There will never be an obstacle at the position where the queen is located. Okay. So on position 4, 4 with no obstacles, the queen can obviously attack 9 squares here, or 9 squares. Okay, and then given 3 obstacles in this case, there are 3, 4, 5, 6, 7, 8, 9, 10 squares that she can attack. So we know the position of the queen. We know the position of the obstacles. So if we have a board representation and we place obstacles into that board state, and then we start at the position of the queen, and if we just brute force move the queen through each of the 8 paths until she hits an obstacle, then we break out of that iteration where we're essentially moving along that path, and then we continue in the next direction available. So for instance, if she had obstacles around all directions, we'd be checking if the queen had obstacles at every immediate square around her. We'd check the square as to whether or not it contained an obstacle, and in that case it would. So we'd break and we'd continue along the next loop. So we'd start out with a number of visited squares as 0, and for every square that we're able to visit until we hit an obstacle, maybe we can increment that total count. Okay, let's see if we can do that. We just need to return the number of visited squares and try to watch out for off by 1 errors. So the first thing that I think we can do is build a board representation. All right, so first of all, what are our variables here? N is number of rows and columns, board side length, and that's a square board. K is the number of obstacles. RQ, CQ is the queen row, queen column location. Obstacles is this 2-dimensional array of ints. So we have something like this, I guess, which represents the location of obstacles. Alright, the board can get pretty big, which makes me a little bit nervous about building an enormous board. But I think it's the most straightforward, well, it's the first solution that comes to mind, is to build a board and then fill it with obstacles, brute force a walk in every 8 direction until we hit an obstacle, summing the number of visited squares. So if we start out with an empty list as a board, and then for I in range n, which is the length of sides, for j in range n, it's a square board. We can represent it as a list of lists. So we can board.append an empty list, and then board at I, we can append some initial state for a square. So we could like append none, or maybe I'll append 0. So for I in range n, so for the length of the column, or length of the rows, let's say, we append an empty list for every row, and then for j in range n, we, at the index I, append a 0. Is that right? Let's print an empty board. And I could probably format that a little bit more nicely. The board, I mean. Yeah, so we have our board. We have a list of lists. Here I want to print We could new line separate the board, the list of rows. So I'd have to stringify a row. If we did this, for instance, string row for row in board, let's see what that looks like. Oh, I need to actually do proper list comprehension here. Okay, so now we have a list of strings, and I can join them on new lines. New line dot join that list of strings. Okay, so we have some kind of board representation there. It's not super important, but maybe it will help visualize. And I'm also doing it upside down, I guess, because it's going to print row 1 at the top, 2, 3, and 4. So we can flip the board backwards. Should look the same. Obviously, we just have zeros. Okay, so we have some way to look at the board, I think. Let's add the obstacles. So obstacles coming in this format. So what I can say is XY in obstacles, board at XY is equal to 1. And so I'm going to put a 1 where the obstacles are. In our empty board, I assume that the boards are not coming in using their index in the two-dimensional array, but they're using their position. The row and column of an obstacle, so we're going to need to say board at x minus 1, y minus 1 to get their index in our array. Let's run. Well, this one has 0 obstacles. I could put a number where the queen is as well to visualize where the queen is. Here we have obstacles at, we have 3 obstacles, I believe. Is this the same example as this? It is. We should just be able to look. There's an obstacle, there's an obstacle, there's an obstacle. Our queen in this case is here at row 1, 2, 3, 4, 1, 2, 3. So I could also show the queen. I could visualize the queen if that would be useful. We don't really need the queen's. The only reason we need the queen's state is the starting point for our walk along any of these 8 paths. So what I'm going to do is I'm going to, in this case, wherever the queen starts, in this case it looks like it's in this location, we're going to walk north until we hit the end of the board or hit an obstacle and count the number of steps that we've taken, which will be global to all the walks. We walk south until we hit the bottom of the board or an obstacle. Likewise, east, west, northeast, northwest, southwest, southeast. How do we know if we've hit the end of the board? We know the queen's location. So we need, the end of the board is the number of square, is the difference between like the end of the board and her location. So we should be able to figure that out for each of the directions. Squares north is equal to the length of the board, which is n, minus the queen's location. In this case, it's 5 minus 4, which is the queen's location. So that should just be n minus the queen's row location, RQ. So that represents the end of the board in the north direction. Square south is equal to just the queen's row location minus 1. So whatever row she's in, 1, 2, 3, 4, minus 1, there's always going to be queen's location minus 1 rows south, I believe. There's a lot to keep track of here, I think. East, all right, so there's some symmetry here. And the board is square, so there's should be lots of symmetry. So this should be minus the column that the queen is in, I think. Yeah, it should just be, it's rotated 90 degrees. So that should be the same. And then squares in the diagonal directions. So here we have the orthogonal directions. And then the diagonal directions, how do we calculate how many squares are available in the diagonals? So it's not just the number of squares in either direction. Like, so say northeast we have 1, because we hit the top of the board before we hit the furthest right on the side of the board. So in this case, it's just the minimum between the two directions that we're headed. And my cat is trying to get into the room. Okay, so for each of the 4 diagonal directions, it's just the minimum of the 2 directions that we're headed. So that would be minimum of squares north, squares west. So northeast would be squares north and squares east. Hey, buddy. Squares southwest would be squares southwest. Squares southeast would be squares south and east. So now we know how far the queen can potentially travel in any of the 8 directions. So we should be able to walk in that direction until we exhaust the number of possible squares or we hit an obstacle. I think that this will be a way to brute force our way through the board. So let's say that we wanted to walk north. First of all, we're keeping track of a total visited, and then we're returning it. And we can keep our board print out up here and maybe just comment it out for right now. All right, so we're keeping track of how many squares we visited, and we need to walk in 8 directions. So could I do a while loop here for each of the 8 directions? Or I could say like while that current index is not equal to 1, sometimes it's easier for me to think in for loops. So I could say for every square, check its value. If its value is 0, then increment total visited. If it's 1, then break, and then just go to the next direction until we've walked in every direction. Walk in every direction. Okay, so for instance, for I in range squares north, we need to start at the queen's current location plus 1 step in whatever direction that we're headed, and check the value. But we need to start at 1 step ahead of wherever the queen is located. And range goes up to, but not including the value. So let's try, I hope that this is correct. All right, so we need to get the queen's current location on the board, which we should be able to get from RQCQ. And again, RQCQ is given to us as the square locations, not the index. So it's going to be a 1 off everywhere. I think RQ minus equals 1. CQ is minus equals 1 everywhere. So now this represents the index in our array, in our matrix, if you will. So the queen's location is RQ, CQ. And we're walking I number of times unless we hit an obstacle, at which point we break. So if we're to brute force this, we're going to walk in every direction, and we're going to walk north. So for I in range 1, squares n plus 1, board where the queen is currently located, plus the direction that we're walking in. That's the current square we're on. If that square is equal to 0, we total visited plus equals 1. Otherwise, we break. And this is the same as saying if not board at this location, then we keep walking unless we run out of board. Okay, so this is also going to be really symmetrical, I think. So if we're walking south, we're walking as number of possible squares south, starting with 1. And we're staying in the same queen's column, but we're going downwards a row. Okay, I think that this is how we're going to do it. East, we increment the column 1. Need to make sure that we can walk east. West, we decrement the column 1. Just to visualize this, I wonder if before I get too far ahead, I should just display the board with the path that's been walked. I could try that. So we're printing our board. Actually, I'm just going to keep walking in every direction before I lose train of thought. So let's walk northwest, which means that we need to go up a row and back a column. So row plus, oh, and this isn't plus 1. Not plus 1, plus I. And northwest, we're going up a column and back a row. Northeast is just the opposite. We're going forward a row and forward a column. Southeast, we're going down a row and over a column. And then southwest, there's a lot of repetition here. Southwest is backwards in both directions. And at that point, I think we've walked in every direction. Northeast, northwest, southwest, northwest, west, east, south. We go north is up a row, south is down a row, east is forward a column, west is backwards a column, northwest is backwards a row, up a column, up and up is northeast, down and over is southeast, down and down is southwest. Total visited. Okay. All right, so we have some errors. First of all, my output is wrong on 1, but we also have a deeper problem because we get an out of range exception on line 79. So index out of range. Oh, I've made a typo. I'm using squares east for everything. Squares, did I call this northwest like this? Yeah. Northeast, southeast, southwest. Okay. That's looking okay. And we have some errors. Runtime error. What is and a wrong answer? Ay. What does the... Let's look at the runtime error. I would like to see this. That is a big board with no obstacles. Let's test this one. Memory error. Yeah. So this board is 100,000 square, which is pretty big, I guess. So I'm building this board. And in doing so, I've got this enormous structure that I'm then looping through 8 times with no obstacles. So we're going through quite a lot of memory, probably just trying to store the board at all. So now I'm thinking that we can't really store the board if we want to do this efficiently. And the question is, do we need to store the board? Intuitively, we don't. I mean, we know we don't need anything of all this space, right? I mean, in fact, most of the space isn't even used for anything. And the space that is used is potentially truncated by an obstacle. So I'm building this huge thing in memory, most of which I never even use. So the question is, what else to do? We know the location of the obstacles. Even if we don't have a board to put them in, we know the location of the obstacles and the queen. And what we want to do is count the number of places in between the queen and any obstacle or the end of the board, which is just a difference between two numbers, 8 in 8 different ways, if you will. It's just the difference between two numbers. And those two numbers are queen's location and obstacle or end of board in any direction. So how are we going to iterate then? If we don't have a board object to iterate over, we do have a list of obstacles. So what I'm going to do is come to terms with the fact that we can't store a board in memory. We do have obstacles. We need to loop over the obstacles, certainly, because we need to know the location of all the obstacles. There are edge cases where, like, if we know the obstacles, for instance, are immediately surrounding the queen, but that's definitely not worth it. We want to loop over the obstacles. We know the queen's location. We know whether or not an obstacle shares a column or a row with the queen because we have the coordinates. We should be able to check actually. We should be able to check actually. Okay, there can also be multiple obstacles in the same row, for instance, in which case we might have to. We still want to get the shortest distance between the closest obstacle and the queen. Closest distance between any obstacle along any direction or the edge of the board. So let's try this. If we share a row with an obstacle, let's look at I need a visual here. If we share a row with an obstacle, then we know it's a potential problem, right? We don't even care about obstacles that aren't orthogonal or diagonal to us. If we share a row with an obstacle, then we want to get the minimum distance between either the end of the board or it, or really the last minimum distance that we've seen along that particular row. Likewise for the column. And then we'll worry about the diagonals momentarily. So for each of the obstacles, if the row that the queen is on is equal to x, which is the row that the obstacle is on. So let's call this row, column. So if we share a row, then the obstacle is either to the left of us or to the right of us, which is a distinction on the column. So if the, I need to keep my variable straight. If the column of the obstacle is less than the column of the queen, then in that case, the column of the obstacle is less than the column of the queen, then we are east of the obstacle. We're going to need to keep in mind how many squares are available in any of the directions still. That's still part of the solution, I think. If we're on the same row, but we're east of the share a row, either east or west of obstacle, then what we want to do is we want to count that minimum value that we've seen. And we want to do that for north, south, east, west, and the diagonals, and then sum that. So in the happiest possible state, we wouldn't have any obstacles, let's say. That's interesting. In the happy path, if you will, we wouldn't have any obstacles, and the number of squares that we can hit is actually just the sum of all of the available squares. So I can update the number of available squares in place as we loop through all of the obstacles. So we can think of these as, available squares. So what we're going to do is ultimately return those squares, and we're going to update them as we see obstacles. Squares east, squares southwest, and if this was code as part of a project, I would not have a line that's that long. So if we share either east or west, then I want to update the number of available rows depending on the current number of available rows in that direction. So we're east, we're going to update squares west. So if we share a row and the column of the obstacle is less than the column of the queen, the number of available squares west now is the column that the queen is on minus the column that the obstacle is on. We still have to worry about off by 1 here, so it's the index is the column that it's on minus 1. So now we've updated squares west. There's no obstacles, we never update them, and we just sum everything. So we've handled west, we need to go in the opposite direction. If the obstacle is greater than the column the queen's on, then we're updating squares east. CQ, column that the queen is on. Well, it's the column that the obstacle is on minus the column that the queen is on. Column minus 1 minus, I think. So this takes care of east and west. If we share a column, I probably don't need to make this so nested. If the column that the queen is on shares a column with the obstacle, and what's wrong here? Okay, nothing's wrong. And then if we're north, so if the row is, or if we're south rather, all right, let's go north first. And row, and this would be row queen. So there's still, there's always going to be symmetry here, which is pretty interesting. So here we have the row queen minus the row minus 1, row minus 1 minus the row queen. And we're updating squares north and squares south. Squares south is if the obstacle is greater than the row that the queen is on. Okay, so just to keep track of what we've done. So we are not needing to construct a board, assuming that this is possible. It must be possible. We don't use hardly any of the board. Okay, now we need to figure out when we share a diagonal, any of 4. And here we'll say if Alright, well there are 4 locations. So what we can say is if the obstacle is northeast, meaning that the row is greater than the row that the queen is on, and the column is greater than the column that the queen is on. So that means that we're in an obstacle already, in which case we are to the northeast of our queen. And we need to make sure that we're square northeast, because we could be any square northeast, but we need to make sure that we are diagonal northeast. So that means that the row and column difference is the same. So this could be a combined and here, or just a nested if in this case. So what that would mean is if the row minus the row that the queen is on is equal to the column minus the column that the queen is on. That's going to be the same for every diagonal, I think. In that case, we have an obstacle in our path. We've already calculated how many possible squares we have in any of these directions, and we're trying to update that. Thought I was going to get hung up on the diagonals. This should be no different. We just need to check if we're square diagonal with it. Get the minimum value, diag length, current diag length, or end of board. No, current diag length or obstacle. If the row that the obstacle is on minus the row that the queen is on, square northeast is always going to be that minimum value. Well, we know we need to update square northeast, and I call this squares northeast. So we always have to do row that the queen's on minus 1 is less than the value of squares northeast. Then there's symmetry among these. The row that the queen is on is this, and the column is less. And here we say if the row that the queen is on, or the row that the obstacle is on, minus the row that the queen is on is equal to, I need to reset here. If we're going northwest, we have an obstacle here. I think it would be helpful to actually name these things a little bit better. Like, what is the row that the obstacle is on minus the row that the queen is on? That's just the distance between them in the vertical direction. It's equal to the distance between these guys in the horizontal direction. Okay, so I think we've walked in every direction. So first of all, let's just try to run this on the sample use cases. Solution.py. Return sum of all these squares. Built-in function or method object is not subscriptable. Okay, so I've got some kind of error in the sum down here. And that's because I'm trying to subscribe to the function sum. Alright, so we should pass this in and pass the list in as an argument. Alright, somehow we passed 2 use cases here, but we failed on sample test case 1. Alright, let's check the logic here very quickly. So the squares available north, we know this should be correct. Northwest, northeast, southwest, southeast. for row, column, and obstacles. If we share a row with an obstacle, let's take a look at this picture. If we share a row with an obstacle, we're either east or west of it. So if the row that the queen is on is equal to the row that the obstacle is on, if the column that the obstacle is on is less than the column that the queen is on, then we are east. So squares west of us is equal to the column that the queen is on minus the column that the obstacle is on minus 1. Oh, did I not offset the queen? Does it need to be minus 2? Well, let's think about this. In this case, the obstacle is on 4-2, the queen is on 4-3. So if in this case 2 is less than 3, which is true, squares west of us is going to be equal to 3 minus 2 minus 1, which is 0. That's correct. If the column of the obstacle is greater than the column of the queen, squares east of us is going to be column of the obstacle minus 1 minus the column that the queen is on. I think that makes sense. If we share a column, we're either north or south of an obstacle. If the row of the obstacle is less than the row of the queen, then we're north. So squares north is going to be equal to the row of the queen. So say 4 in this case, minus the row of the obstacle, which is 2, minus 1 for the offset, and we have 1 square available. So that looks correct. Likewise, if the row of the obstacle is above the queen, so let's say the obstacle's on 5-3, then we would have squares. Wait, if the row of the obstacle is above. Oh, these are backwards, I think. Right? If the row of the obstacle is less than the row of the queen, then squares south is equal to this, and squares north is equal to row minus 1 minus row of queen when the row is greater than the row of the obstacle is greater than the queen. Okay. Hopefully this one works, and we're coming down to 1 minute. That would be nice. Oof. Still messing up some cases here. So we're getting the wrong answer. We're not getting any runtime errors, meaning we're probably not running out of memory. So let's take a look. And let's put this into the custom input. We're expecting to get 40 out. We're getting 54 out. So let's check the logic specifically along. Well, we'll check all the directions. If we share a row, yeah, this looks, we just checked these. If the row of an obstacle is greater than the row of the queen, if the row of the, so we share a diagonal, so we're northeast if the row is greater than the row of the queen and the column is greater than the column of the queen. Then we check to see if the row that we have minus the row that the queen is on minus the column that we have for the obstacle minus is equal to the column of the queen. Then we're on an important diagonal. And then we get the minimum value along that path. Oh, here I'm not actually getting the min value for my orthogonal directions. I'm not checking. So if the column of the queen minus column minus 1 is less than squares west, likewise on checking in the west side, or the east side rather, if CQ, or rather col minus CQ minus 1 is less than squares east, I need to do the same for north as well. Still failing. And we got a runtime error. These all runtime errors? Yeah, let's see what the runtime error is. CQ is not defined. RQ is not defined. This naming. It's my fault for not paying attention. All right, let's try to submit code again. Still failing. And we get the wrong answer. So expected output to be 40 here. And we're giving 54. Oh man, I made all of these if statements. So I need to make sure that these are else if statements. All right, so let's double check. Now we'll double check if we share a column and we're either north or south of an obstacle, if the row of the obstacle is less than the row of the queen, and if the row of obstacle minus the row of the queen, that's backwards, is less than squares south. Likewise, I got north and south backwards here. Because if the obstacle is north of the queen, then we want the row of the obstacle minus the row of the queen minus 1. All right, I hope I didn't mess that up on the diagonals. And I still have my old code in here, which I need to remove. And I have a typo here with squares southeast. And so let's run this. This should be 40 if it works correctly. And we get 40, so let's try to submit this solution. Okay, finally, we pass all of the test cases. That was a bit harder than I thought it was going to be, honestly. So, lessons learned. 1, take a look at the size of the potential problem space and consider not putting stuff into memory if it's not necessary, because you probably run out of it. Other lessons learned: probably watch variable naming, especially when you're using a lot of abbreviations, because I got hung up for a little bit there just reviewing the code and not realizing that SQ underscore is not the same as squares underscore. And in general, I think some of these algorithmic problems are kind of just hard to interpret once you've written them out. So I think there's some benefit to working quickly and keeping the thread fresh before you stare at it for too long. And yeah, other than that, this was pretty interesting. I should have probably realized sooner that the entire board space isn't necessary for solving the problem, given that we're concerned with essentially minimum distances between integers. and not state representation in any way. So I'll have to keep that in mind for future problems as well. Anyway, thanks for watching. That was kind of fun. Maybe next time we'll try a hard problem if I have a little more time. Or maybe we'll just keep going on these medium problems for a while. I'd also be interested in trying out some new languages. Maybe we'll try the next one in Rust or C#. In any case, hope you're having a good time. Hope you're healthy, and I'll see you next time.